everybody. My name is Alex Paradin. I'm the group reporter for Group 3 for last week when we were doing the Rankine cycle. The group leader was Elizabeth Showers, and our other group member was Elon Rosenzweig. So just to give an overview of what we did for this experiment, we were simulating a power plant, so something like a power plant based off of the Rankine cycle for power production. And we were looking at the principles of the Rankine cycle and also the thermal efficiency that comes from that cycle. The apparatus included a water tank that was feeding into our boiler, that was creating steam to feed into our turbine to then be cooled off in our condenser, and tried to collect as much as we could back from that. And so the procedure, just quickly go over it, was that we inspected the apparatus, then turn on the fuel and the water supply, turn on the boiler, and put on the rheostat resistance, and then waited for a steady state before taking measurements. Just to go over the equations we'll be looking at through my calculations, using Kirchhoff's law relating heat input to the specific heat of the fluid, and also the change in temperature that occurred with that heat input, and then also general efficiency, which is that the efficiency when you pull the desired output over the energy input. And we'll be looking over specifically a variation on it for the Rankine cycle, which is 1 minus the heat that we are rejecting in the condenser over the heat that's put into this boiler. So this is, I'm going to be going through a few slides of the different plots that I put together for the values that we recorded during the experiments. What I really want to point out is that for these green lines, that's the start of our considered steady state condition where we started drawing power on the system. The red square, that's our reference point when I talk about any calculations that I do. And I want to point out that, as you can see at the start of the steady state, it's really balanced out, it's very level, it's very consistent with the temperature in the boiler and also the temperature being fed into the turbine. But as we reach the end of our steady state area, which I assume is whenever we start running out of water for the boiler to feed with, you can see that it gets quite sporadic and starts changing this, and so it's not a consistent feed from the turbine, which then makes our power output sporadic. So as you can see, across all of these, very similar thing where it's very steady for the most part through the steady state at the beginning, and then at some point it becomes more sporadic and then quickly takes off and changes value to where we can't use it anymore. And that's why we have to then cut off our power production and reset up our experiment. Once again, same thing. All right. These are all the values that I use to calculate all of my, my calculations. This is all from the reference point that I pointed out for the red square. And so I pointed out here that these are assumed because our experiment, the apparatus was not available whenever we went to run our experiment. And so we had to instead be given these values from the manufacturer. And one of the things that was not included was how much water they put into the system over the duration that they ran, and then how much also they got back out and condensate. So I made an assumption that we were supposed to start with 5,500 milliliters. We weren't supposed to run through all of it because, as you saw, whenever the system starts to run out of water, it becomes unreliable. So I assumed that they ran about 3,000 milliliters of water, and that they recovered about 1,500. That's just going to be the assumption moving forward. And then these are for our various states throughout the experiment. So we have the pressure, temperature, and the enthalpy associated. So like we have for our TS and pH diagrams, as it goes through the cycle, a different enthalpy is associated with it. And so we have the top left, after the boiler, top right is whenever it gets to the turbine inlet, which you can see it actually does have a quite significant temperature drop. So a lot of heat loss through the piping. And after it leaves the outlets for the turbine, not so much temperature loss, but a good amount of pressure loss. Condenser inlets, we have some more, I assumed that there wasn't going to be much of a change there. I didn't see much change. And then condenser outlets, I assumed that all the pressure that was built up after the turbine would leave whenever it hits atmosphere. So this is, again, like I was saying, our diagram cycle. So all the previous enthalpies would be plotted on there, and that's the idealized cycle on the left, and this is the non-ideal cycle on the right. So just to talk about some sources of error from our data collection, the frictional losses that are associated with the fluid traveling through these pretty thin pipes, there's a lot of fluid friction, which can then lead to energy loss. and also the frictional loss in the turbine as it's rotating. That's more losses that we have. Heat losses to the piping, like I said, there's a major heat drop from the boiler to the turbine, and so then that changes our enthalpy value at that point. And then also, I assume there's going to be a good amount of heat loss just in the turbine as it's going through the process of spinning the turbine. Also, like I said before, this data came from the manufacturer. We didn't run the experiment, so I can't be certain about, say, the fluid that's running through the process. Luckily, most of the values that I calculated for enthalpy change across a piece of equipment, they are independent of the flow rate, and so it wasn't much of an issue. And then obviously, idealized versus real. This is the real cycle is off of the idealized cycle lines. It has greater entropy in certain points, lesser entropy, and certain assumptions don't line up. And so in conclusion, what I found was that the prediction for the efficiency for the entire system would be somewhere around 9%. I found it to be, based on this calculation, closer to 18%, which could be attributed to some of the losses and problems coming in the turbine, and so there's more heat that needs to be rejected in the condenser, and then the different enthalpy changes across the piece of equipment. The boiler, there was a lot more heat input from the fuel than was originally assumed, probably because we didn't have a reliable fuel flow assumption. Condenser was very close actually in agreement, and then the turbine again, probably frictional losses, different heat losses made it less efficient than the actual.